I will introduce the first speaker now. And Paolo Di Pietro is currently Senior Technical Education and Know-how Manager at Office Maccaferri Corporate Headquarters in Bologna, Italy. With a degree in Civil Hydraulic Engineering earned in Italy in 1984 and over 30 years as professional in design and construction of geotechnical and hydraulic engineering works. Paolo's experience stated as project design engineer at the lead of a technical engineering team, supervising and coordinating studies from feasibility to final design, performing cost analysis, and overseeing construction sites. Having served for 4 years in the USA as a technical director for the North American operation and later for another 4-year term as technical head of the German operation group headquartered in Berlin, his responsibilities include research, development, and innovation of new steel wire and geosynthetic systems as well. Since 2001, Paolo holds frequent seminars and workshops to design engineers, contractors, and state officials in geotechnical, soil retaining structures, slope stabilization, river and erosion control works, and best management policies and practices of soil bioengineering systems. He is also an active contributor to the development of international standard ASTM, EN, DIN, and author of several papers on international conferences. So it's a great privilege for me to welcome Paolo Di Pietro, the Senior Specialist Corporate Technical Division, Maccaferri, to deliver this lecture on this session on score and erosion. Over to you, sir.
Thank you, sir.
Hello. Can you hear me?
Yes, sir. Yes, sir. We can hear you.
Okay, good. So let me put on the presentation. So good afternoon, everyone. This work is an overview of some basic principles to take into consideration when designing river engineering structures. I'm going to start with a brief background on basic principles of modern river engineering, and I will then briefly classify typical erosion phenomena based on experience and observation. Then I will show an overview of main applications in use for erosion control in river environments along with their functions. And I will then discuss recent research studies and new design approach for the stability of erosion protection systems. And lastly, I will show some real-life project cases with their peculiarities and their challenges. In the history of river engineering structures for erosion control, the first ancestor of the modern gabion dates back almost 130 years ago, when a riverbank restoration along the river Reno, crossing a small town, took place. The small town is today part of the suburban area of Bologna in Italy. You can see here a little bit the location. This early application was built in 1894 to repair the riverbanks due to a breach caused by a major flood. The structure is the first example of how engineering combines the use of natural materials, the stones, confined inside a cage to reduce their size and the overall volume. A simple idea revealed to be successful over the time. The good performance of this application and the many more built in the following years led to further improve this idea through an industrialization of the technology by manufacturing standard geometries with a box shape, standardizing size, quality, shape to allow them to be connected together. These pictures show gabion applications in the early days. At the beginning of last century, the manufacturer introduced the double twisting process of the mesh to provide an improved strength and to allow an engineered use in hydraulic and geotechnical applications. Gabion applications started becoming attractive as engineered systems to control erosion due to their ability to combine the strength, the flexibility, and a natural pleasing outlook at the same time. The picture below on the left shows gabions used to protect the pier in a harbor in the early 60s. The increasing interest for these natural systems led us to invest in research programs aimed at developing design criteria to provide engineering methods to design them against the effect of hydraulics and the hydraulic and geotechnical instability, analyzing performance. Among their best features, the environmental friendliness and the ability to integrate with surrounding environment becomes an attractive subject of research in the 90s. The picture below on the right shows the old site in Italy after more than a century, where the first gabions were used. A few more gabions were added on top of the old ones to raise the bank in the 60s. Nature has fully taken over, and gabions and old and new are blended with the environment. But I would like to mention some basic principle when designing river works. The first postulate we learn from experience is that the hydraulics is not an exact science. When we design structures in river works, we make our choices on current knowledge, but also on know-how and on best management practices, assuming that natural events like rainfall, flooding, storms, to assume in our design will be based on statistical data. This will require caution, a cautious approach, and in most cases to perform a risk analysis, analyzing scenarios beyond the design data assumed. So a modern and correct approach to river engineering requires to recognize two main types of requirements. The hydraulic requirements, meaning the base of technical knowledge, including evaluating the stability of a solution both from geotechnical and hydraulic point of view, using correct and sound engineering practices, using design methods based on risk assessment and not on fixed numbers, considering how erosion will affect the surrounding environment. So in other words, use an integrated river management approach. But also, and most importantly, the environmental requirements, meaning consider the river as a living environment. That requires to understand the rules, like the river is a dynamic environment. It's necessary to consider that it will change over the time. In applying river engineering principles, minimize changes in the morphology and nature of the watercourse. In applying protection measures with proven ability to recover and to reestablish the natural conditions. That is, using sustainable systems. And finally, to provide solutions aimed at balancing the ecosystems. River engineering requires to start from location, characteristics of a watercourse, depending if we are in the mountains, or at the foothills, or in the valley, close to the river outlet. The three regions will be characterized by different climates, different soils, different morphology. In mountainous regions, watercourses will be characterized by steep gradients. Normally, we consider 5 to 10 in the normal practice, 10% in the normal practice. With deep erosion, frequently characterized by an abundant and coarse bedload. Structures used to prevent erosion in these regions are grade control weirs, for example, sometimes combined with secondary longitudinal bank protection. On the mid-slopes, gradients become moderate, so we could consider 1 to 5% as a reasonable standard range. And river sections start widening, forming a low-flow section, a tholweg, and a berm on the lateral sides, which will overflow during the high floods only. In dry times, sometimes forming a small island or rapids in short reaches. Typical structures may still be gabion weirs with a wider crest, combined with bank protections alongside, and small groins to facilitate the sedimentation on curved reaches. Valley regions are the last segment of our river, where the watershed has collected most part of the rainfall volume. Rivers are typically characterized by low gradients, less than 1%, low velocities, less than 3 meters per second, and large discharges, more than 1,000 cubic meters per second. Definitely in larger rivers, we're talking about the tenths of thousands of cubic meters per second, and by a tendency to meander. Intervention in this region will be primarily to stabilize the river banks on bends or straight reaches and to favor sedimentations in sections where meandering tends to progress. The problem of floods in natural watercourses may require solutions like to intervene on the banks, so a bank protection, to build a new embankment, a dike. Alternatively, when space allows, an encroachment area where water may temporarily flow into may be created, so a detention basin. We have seen that in the mountains, we may alternatively consider to reduce the gradient, so a gradient reduction. In other cases, a cross-section reprofiling may also be an option. In case of a bank protection required, the top of the slope may be sometimes raised when little space is available on the sides, or otherwise a section may be widened to convey a larger amount of discharge within the river section. All this shall not forget the possibility to encounter site limitations like archaeological landscape restrictions or other environmental issues. As previously mentioned, depending on the site, location, geometry of the site, climate, etc., the engineer shall choose the most suitable technology, varying from a large, massive retaining structure, or a hard armor, or a soft lining system, or even simply by using natural self-sustaining soil bioengineering practices to help fast and natural recovery. Understanding rules means to understand how erosion generates. We could start from the type of problem, then see what is the case, the cause, and where is it generated, and finally, which effect results from such type of problem. We could have drainage resulting in surface runoff, typically occurring natural or artificial slopes, and finally generating erosion due to lack of vegetation, soil instability. Another type of problem is seepage, resulting in reduced soil strength, where? In embankments and slopes. Another problem is scour, formation of scour holes at the toe of riverbanks critical for bridge abutments, generating progressive instability. Finally, the wet and dry cycles or temperature variations, resulting in the formation of cracks in cohesive slopes, resulting in progressive debris. Erosion protection systems in rivers can be grouped either depending on their direction to the stream, lengthwise or crosswise, meaning along or across the riverbank, to prevent instability, or by conveying the flow as a drainage media. Sometimes they can be intermediate between longitudinal and transversal to the stream to control the meandering by favoring sedimentation. In the first category, we can consider bank protections and bridge abutments. In the second category, we can group river crossings like culvert head walls, as well as guide bunds, more typical of some larger rivers, or bridge piers. In the third category, we can group channelized streams or reaches where the rivers are canalized due to the space constraints typical of the watercourses crossing urban areas. And in the fourth category, we may refer to the groins to maintain the flow within a given path. Along the banks, rivers generate instability by eroding the toe and creating a failure surface. The solutions in this category may require mass gravity walls or linings, depending on the angle of slope. When infrastructures cross rivers, we shall ensure that the bridge has a stable foundation. We can see examples of progressive erosion underneath the bridge due to the lack of protection. On the right side, examples on how the main structure can be protected. Another example of lack of protection in a culvert structure. Here, the main contributing factor is the progressive erosion is the rigid apron, unable to follow the soil contour. The correct design shall consider flexible systems able to manage the transition zone between concrete, rigid, and soil, loose and erodible. Special applications are guide bands, frequently used in the Indian region. Guide bands are structures that divert the water to flow in the central zone of the river to avoid river meandering across the large floodplain with risks for all piers to have excessive scour due to the low flow season, during the low flow season. Pier foundations are highly erodible riverbeds in highly erodible riverbeds. They can be subject to instability as piles are progressively exposed to the flow. These situations are still quite critical as we have rigid supporting elements, the piles, in contact with the loose erodible soil. An adequate protection with flexible structures to manage this transition, avoiding abrupt changes will also be needed. Drainage channels like channelized streams collect and convey the water to a safe zone. Protection measures in these courses guarantee that the flow is safely brought to the delivery network. In large floodplains, normally the groundwater flow as well as the secondary channel may affect the flow in the main channel section sometimes, forcing changes in its path. Considering that floodplains or areas adjacent to the main channel are often used for agricultural purposes in the dry season, gravity walls or revetment may be used to contain the flow inside the desired section. Often in wide river sections, typically in alluvial plains, where meandering can be dangerous as it could progressively scour close to the infrastructures, groins may be used to favor sedimentation in other reaches at the bed. Lateral spillways. They are used to provide a controlled water release, diverting the water flow in the river from the river during the flood, or redirecting the water back into the river after the peak flood. Spillways release water to prevent damage to the levee embankment. Except during the high water event, the water does not flow over the spillway. So spillways can be constructed with the crest lower than the top of the embankment. The protection is usually made by concrete, stones, rocks, or gabions. Overflow spillways with significant hydraulic head will require properly shaped crest, an energy dissipator downstream, and a protected release channel. Gabions and matrices are flexible and permeable structures frequently used in river engineering works, as we have seen. It is in 1984 that gabions and matrices become an engineered system after the first experimental study done by Colorado State University. Back in 1984, there were no rules about erosion protection systems. The mattress stability was based on the principle that the confined rock should not move. The proliferation, actually, in the hydraulics of open channels, an important change over the years has been the creation of standard. The proliferation, as I was saying, of several types of erosion systems required engineers to provide a guidance for their selections to guarantee an effective protection against erosion. In the United States, the most reference standard defining performance limits for all erosion protection systems in open channels is ASTM D6460. Applicable to most types of erosion protection systems, from the heavy duty to the light revetments, this standard defines the stability for aligning either when no collapse or when limited erosion underneath occurs. In order to reevaluate the conditions of failure in line with an ASTM for the new Maccaferri mattress, Colorado State University recently completed a research study performing a new test campaign. The research was developed in 4 steps. Task 1, preliminary. was aimed at analyzing the effect of the flow on the wire mesh and the tile only. To this was performed running the flow on an empty mattress. The scope was to see how much resistance to the flow the wire mesh alone provide. The task 2 and 3 combined, always preliminary, were made filling mattresses with rock of different gradings and uniformity. Here the combined presence of different partitions and stones allowed to test the velocity dissipation through the mattress layer. Task 4 was made on a larger flume, simulating the real flow regimes of an open channel. Based on results of the preliminary investigations, the best performing combinations of partition and stones were chosen. The tests were performed in line with the requirements of ASTM, which defines failure either by a recurrence of a mechanical rupture or by reaching excessive erosion under the mattress. The development of all 3 project phases required a thorough analysis of the various aspects. All in all, the research was completed in almost 3 years, requiring important financial investments, but also in terms of time and resources. On the other hand, the results brought up to light quite a valuable outcome, as overall the effectiveness of the best performing mattress resulted into a 73% reduction in thickness of a bank protection compared to a conventional riprap lining. The new research at Colorado State University allows to introduce a correlation with other factors not considered in the past, allowing to optimize limit performance on the new mattress, ultimately leading to the definition of the new approach applicable to the new generation of Maccaferri mattresses, the Rhino Mattress Plus with the X ties. The Rhino Mattress Plus with the X tie has basically 3 main improvements compared to the standard Rivet mattress. One is depleting of the mesh, making partitions much more robust with the double mesh. Second is the innovative and much more durable new polymer coating, making wire mesh more resistant to the abrasion and the sediments carried by the water, a higher UV resistance to the high temperatures, as well as a much lower embrittlement temperature to the cold climates. And finally, the X-tie, a patented anchoring tool to firmly and securely connect the lid to the bottom of the mattress. We learned that the benefit of a double diaphragm partition, the rock size smaller and more uniform, and above all, the presence of a tightening connection between base and lid greatly boost the performance both against rock movement and against erosion. By interpolation, we could introduce partial factors in the Shields formula to include these contributions. Here, we can see the formula here. In summary, comparing past and present in our design approach, we could say that the attractive force theory allows to define equivalent Shields coefficient to apply to mattress protection. This method, still in use for riprap, is focused on the limits of the lining's mechanical stability, condition of no movement of the stone. The new standard ASTM introduced a new way of looking at the performance of an anti-erosion system. The mechanical stability, always, combined with the controlled or limited erosion underneath, which is the main purpose of it. This chart shows a summary of where we can observe the relevant improvements of the allowable shear stress in relation to the thickness of the protection when we combine mechanical stability and the anti-erosive function. The light blue color bars show results of standard mattresses with single diaphragms based on the tractive force tested in 1984. The blue middle bars show the increase in shear strength by using a double pleated diaphragm only and the most suitable grading for the film. And finally, the dark blue bars show the ultimate and most relevant increase in shear strength when adding the X ties to the unit. So overall, we have say an over 50% increase in performance. These results today have been implemented in the new Macro Studio, a user-friendly software to assist designers in the selection of most appropriate solutions for riverbank protection. To enable designers to view different scenarios, the software provides multiple choices, pulling out from a database shear resistance values for other common anti-erosion systems as well, allowing also a choice to model a channel section only with natural materials like bare soils or vegetation from light to dense. When choosing Erinometrus Plus, the software will require the relevant parameters to use, like the grading for the rockfill, the thickness, and the assumed roughness. Based on these variables, a database will provide the equivalent allowable shear resistance for that mattress configuration. Macro Studio is a simple tool with a user-friendly interface, able to model open channels of any shape, from simple trapezoidal to double trapezoidal, or virtually changing geometry, checking multiple discharges, or profiling slopes, partly with natural vegetation and matrices or gabions, is very simple to do. Results allow the designer to quickly make a decision considering various scenarios and best performing configurations. Sorry, I have to plug in. Okay. We provide regular training online sessions on Macro Studio for people interested in using this tool. Let us now move to the last part of this presentation, a brief overview of 5 interesting case studies in the Indian territory. The first one is the Mahanadi project. The location of this project is in the eastern part, eastern side of India, in the Orissa state, near the town of Paradip, south of Kolkata, where the Mahanadi River flows into the ocean. After the cyclone of 1999, both rivers Devi and Mahanadi suffered from severe erosion. The effects of the tidal waves, combined with water velocities of 2 to 3 meters per second, dislodged the existing protection works. The project received financial aids by the World Bank. The riverbanks needed to be reconstructed using the available fill. The 2-to-1 slope was stabilized by dumping loose rocks, riprap, on top of which a lining protection of 0.5 meter gabions was installed. A large part of the protection had to be installed underwater, and that was one of the biggest engineering challenges. Gabions had to be pre-filled and launched by crane down to the riverbed to a depth of 15 to 18 meters, so quite a challenge. Cost effectiveness was one of the successful project's outcomes. The second project is the Valmikinagar project. This location is on the northeastern side of India, very close to the border with Nepal in the Bihar state. The Bihar Water Resources was looking for protections on the left bank just upstream of the Gandak River barrage in Valmikinagar. The Gandak River in this section has a discharge in the range of 24,000 cubic meters during the monsoons, resulting in severe erosion on the left bank and damaging the gates of the Gandak barrage. So approximately 1,080 meters length of the bank had to be reconstructed and protected. The retaining structures was designed for a seismic zone of 5 as per the Indian standard. The retaining structure required to be flexible, permeable, and able to withstand poor water pressures and protect against scour. So in order to meet these requirements, the solutions was divided into 3 parts, in 3 sections. The reinforced soil retaining wall with a permeable gabion fascia, the slope stabilization on the upper bank with a synthetic erosion control geomat reinforced with a double twisted mesh, and finally the scour protection with a mattress apron and a gabion key. And this solution was chosen because of the high permeability and flexibility and the environmental friendliness. You can see here some details of the structure. The soil reinforced structure was used combining geogrids, high-strength geogrids, and steel wire mesh, a soil reinforced system with a gabion fascia. The third project is the Golpaganji project. This is approximately 100 miles south of the Valmiki along the Gandak River, near the city of Golpaganji. Another project which required an intervention of erosion protection. Here, during the construction of a bridge across the Gandak River, due to a sudden increase in discharge, the river started eroding the bank at the toe of the guide bund and downstream and at the downstream end. Riverbank protection measures required, in this case, urgent protection works, using the available sand and least amount of stones, scarcely available in the area nearby. To meet this requirement, cylindrical gabions lined with the geotextile and filled with locally available soil were proposed. Here you can see a picture during the installation of these units. Gabions were factory assembled and supplied in a folded form. Construction required opening and holding gabions to allow fast filling using special arrangement designed to this purpose. The protection was was completed and say in a very short time, and it was extremely successful. The fourth project is quite a challenging project. This is the Budge Budge project. It's because it's about is quite an unusual effect, the tidal bore. The location is in the suburban area of Kolkata in the southwestern side in West Bengal. The Cheviot Group has a factory located along the river Hooghly. The river is in this section in its estuary zone, and it is subject to heavy tidal bore phenomena, which cause intense turbulence and hydraulic jumps. Here you can see a couple of pictures of, say, during it was approximately 6 meters in height, and the slope at a 2:1. The thickness of the system was analyzed and considered to be approximately 3 meters. Geotextile bags and sack gabions filled with sand were adopted to fill the embankment core. Here, this part. The geotextile bags were made of woven polyester geotextile material. Sack gabions lined with geotextile were filled with the dry sand and laid in position. In order to ensure solid and firm function to the gabions used at the toe protection, an additional high-strength geogrid reinforcement was wrapped around the units. The two lower images show the protection on the embankment before and after the installation of the upper gabion layer to cover everything. Last project to mention is the Delhi Noida at the Yamuna project, the Yamuna River project. The location is south of Delhi in the suburban area. In 1999, the Delhi administration proposed a road bridge across the Yamuna River downstream the existing interstate bus terminus bridge for the mass rapid transport system about 2 kilometers upstream of the existing Okla barrage. Due to the presence of the new structure, it was anticipated that velocity would be high and the bridge piers needed a protection. The river works were designed for a discharge of 15,000 cubic meters per second. And the maximum velocity is around 3.3 meters per second. The original design consisted in a massive slope protection with a 1 meter thick gabions, stones, with a cost estimate of about 275 million Indian rupees, around 6.1 million USD. The alternative proposal considered was to use a single layer of 0.5 meter gabions. And here the interesting point, because this resulted in a volume reductions of about 50% as compared to the original solution, resulting into an overall saving of nearly 130 million Indian rupees, accounting 2.8 million US dollars approximately. So quite a considerable saving. So in conclusion, in this presentation, we have seen important points, I guess. Number one is erosion is a result of a natural environmental change. We shall understand the rules to develop sustainable solutions. Number two, river works require solutions suitable to integrate with the surrounding environment, minimizing disturbance with the ecosystem. Point number three is a very important point, is an achievement of these days, of modern times. Erosion control systems shall be tested in accordance to a common standard procedure. Thanks to the new development currently in the ASTM standard allows to do so. And this is the first guideline for most systems. Results for new rhinometers show an effectiveness by going in accordance with this ASTM of over 50% compared to conventional riprap. And when I mention 50%, I'm referring to the total cost of ownership. So that includes construction, maintenance, and everything. So during the lifetime of a structure. And the number of projects built around the world, we have seen a few examples in India, prove the effectiveness of these erosion control systems, as well as their environmental friendliness, of course. Well, this concludes my presentation. Thank you for your attention. And of course, I am more than available here to answer your questions.
And the current protection methods help in prevention of soil from the effects of heavy floods, as the heavy floods that occurred recently in the northern and northeastern states in many regions to submerge underwater.
Yes.
So that was the question. The methodology can be adopted when there is heavy floods, especially in north and northeastern states.
Yes, absolutely. Thank you for the question. Yes, the procedure here that we are putting in place, and I was fortunate to be also one of the members in developing a ASTM D6460, allows exactly to apply to any erosion system the effect of a flood, basically, because we have all the abilities during the testing procedure, and ASTM allows that to define different slopes. So we can even design for a spillway generating the right amount of allowable shear stress, which is, let's say, simulating the realistic scenarios. So yes, my answer is absolutely.
Thank you very much. Any more questions from the audience? So there is one question from Alok Ranjan that you have referred a river near Gobalganj in Bihar. Are the soil conditions different from whatever you encountered in Valmiki Nagar? So the question is, you have referred a river near Gobalganj in Bihar. Are the soil conditions different from whatever you encountered in Valmiki Nagar?
Yes, I think you can also see it a little bit. Maybe the pictures were not large enough to see a little bit the difference. But in the Golpaganchi site, we had to deal with, say, quite a big challenge, the scarce availability of rocks. And so that was, in practice, the challenge of that requires us, instead of having a lighter system with mattresses or gabions, depending on design, but we had to go on a 3-meter thick embankment, which required, of course, a little bit more substantial volumes, but we were able, by using geotextiles lined inside a cylindrical gabion, to create the solid core of the embankment.
Okay, so I think it's clear. Now there is one more question from Smith Patel. Is it necessary to take seismic zone-wise design based on the seismic condition? Whether we have to accommodate the changes in design is the question from Smith Patel.
Yes, seismic is an important factor, because it may generate also soil liquefaction in certain instances. Not always, but of course it has to be considered based on the geometry of the site. If we're speaking of a retaining structure, definitely is a must. Is one of the conditions that would lead the design to a certain type of solution and reinforce, or say we have a massive structure, we need to do, let's say, in line with the requirements. If it is for a slope, depends on the type of soil and on the sloping angle to decide whether seismic can or cannot or shall not be necessary to consider.
Yeah, there is one additional question from Anand Hulagabali. The question is that gabion walls or sand-filled geotextile bags, which will be more stable and economical?
Typically, I would go for gabions in a box shape, let's say in box-like shape, because this gives for the above the water construction the possibility to connect the units together. Cylindrical gabions normally are used for the underwater applications in any type and shape because they are easy to install. Even though I must say that after, and you have seen some of the interesting and most challenging projects. There was the first one that I show in Hanadi, where by the use of a suitable crane and skilled labor, we are able to lift units in a box in a typical shape of a gabion box. So this means that when you're placing the units in underwater, you can also achieve quite a uniform surface on the ground, and this obviously benefits the anti-scour function.
Okay, we got the point. Now from Shankar Ganesh, there is a question: if suppose the embankment upon soft soil as well as in the heavy rainfall area, for this case, is there a possibility of slope surface erosion and slope deformation also? Which will be a preferable solution?
So deformation or what is the
slope surface erosion or slope deformation also? What is the preferable solution? Embankment on soft soil, when heavy rainfall is happening, there is a possibility of slope surface erosion as well as slope deformation. So which will be a solution in this particular case?
Well, it is generally difficult to give an answer that would fit all points, because this would very much depend on the site conditions. The approach we use is generally to understand the level of deformation that we have to achieve, and depending on this, we might combine the use of geosynthetics and steel wire mesh together. There are several solutions that we could use for that purpose. The use of high-strength geogrids combined with the permeable and flexible units in steel wire mesh. So this could be, if I'm trying now to follow a potential project. Now this could be an option. Yes.